Behind me is a very special 2D shape. It's called an ellipse. You might call this an oval, but mathematically it's called an ellipse. Now, you might also think of an ellipse as some sort of squished up circle, maybe. However, there is one definition that helps us properly determine what can qualify as an ellipse. Now, obviously, it must be round, so it cannot be some sort of square or rectangle, but there is one definition that nails it all together. Essentially, in an ellipse, there are two special points, and these are called the focus points. In plural, we actually call them foci. Okay, so just keep that in mind. Now, because they're called the foci, I'll label these 2 points F1, F2. So these two focus points are very special. Basically, if you choose any point on the ellipse, so for example this one, and we'll call it X, no matter where you choose X on the ellipse, if we were to connect F1 to X and F2 to X as well, then we have the property that F1X plus F2X is always going to be constant, no matter where X is selected on the ellipse. So I chose X here. I could have also chosen X to be here. X could also, be here. No matter where on the ellipse I choose the point X, this sum will always be equal to the same constant value. It follows that if you were to choose some point in the ellipse, call it Y, and you were to play the same game, connect F1 to Y and F2 to Y, then that might not look like a very good connection, but it follows that F1Y plus F2Y is going to be smaller than the constant than that we had over here. And you probably already guessed by now that if you were to choose some point outside the ellipse and then, connect that point to the two foci, it follows that F1Z plus F2Z is going to be greater than the constant that we described over here. Now, the value of this constant can basically determine how big the ellipse is. So it can be something like just 1, or it can be like 2. Basically, the value of this can determine what the size of the ellipse is. The ellipse also has a very special property that we have not discussed about. In particular, if we consider an ellipse, and of course its foci, and also a line tangent to the ellipse at point P, then if we were to connect F1 and F2 to P, it follows that there are two equal angles created on both sides of the segments that we drew. So this angle over here is equal to this angle. Now, I think the fact itself is pretty cool. However, the proof is even more elegant, I would say. So let's dive right into it. The proof begins with reflecting this ellipse over the tangent line to obtain this one. Now, I've labeled the reflection of F1 as R1 and the reflection of F2 as R2. Now, the line segment I care about is the one connecting R1 to F2. And I'm going to consider the point of intersection between R1 and F2 with this tangent line. So I'll label the point of intersection as point Q. Now, I'm going to make a claim. I claim that point Q, so this one, is actually the same as point P. Now, I know it doesn't look like that visually, but I've intentionally drawn it like this to help you reason through the contradiction a bit better. Well, first suppose that P is not equals to Q. Then we'll try to derive a contradiction. If Q is not the same as point P, then Q must be outside of this ellipse, right? Because the only point that is on the ellipse that is on this line as well is point P. So anywhere else needs to be outside of the ellipse. Therefore, let's consider connecting F1 to Q as well. So let's connect F1 to Q. Now, consider this. Consider connecting F1 to P and also F2 to P, right? we know that because Q is outside of the ellipse, we know that F1Q plus F2Q is greater than F1P plus F2P. Again, because P is on the ellipse and Q is outside the ellipse. Okay, that's cool. Now, observe that F1P is actually the same as R1P because this is just a reflection of this. I'm going to interject because I meant to say that F1Q is equal to R1Q. That's because they're just reflections of each other. Now, the fact that F1P is equal to R1P is important. However, we'll actually be using that fact later on, so sorry about that confusion. Anyways, continuing on. Therefore, we can replace F1P with R1P. Okay, that's great. Consider triangle R1P F2. Consider that triangle. You might have to squint a little bit, but you can see that there is indeed a triangle connecting R1P and F2, right? By the triangle inequality, we know that R1P plus F2P, this is going to be greater than R1 F2. And once again, because of the triangle inequality, because if you were to choose two sides of a triangle and you take the sum of their lengths, it must be greater than the length of the third side that you did not choose. So in this case, R1P plus PF2 is greater than R1 F2. Now, we know that R1 F2, this is equal to R1Q plus F2Q. So we can write this as R1Q plus F2Q. Now, can you see the contradiction here? Consider this inequality that we derived and this separate inequality that we also derived. Notice that R1P is actually the same as F1P because R1P is a reflection of F1P. Therefore, over here, we may replace this with F1P. Okay, so now take a close look at both of these inequalities that we've boxed. I'll call this inequality 1 and this inequality 2. All right. Notice that inequality 1 is the direct opposite of inequality 2. It's contradicting inequality 2. In fact, these two inequalities are contradicting each other. Over here for inequality 1, we're stating that R1Q plus F2Q is greater than F1P plus F2P. But over here in inequality 2, we're stating that F1P plus F2P, this is greater than R1Q plus F2Q. Directly opposite, a contradiction, and therefore P must be equal to Q. So from our claim, we can actually say that F2, P, and R1, they are actually collinear. They actually lie on the same line. And because F1, P, and R2, that's created by reflection, these 3 points are also collinear. So we can now begin our angle chasing. We're going to consider this angle over here, okay? And we'll call it theta. Now, by opposite angles, this angle over here is also theta, right? It's opposite angles. And this angle over here is also theta because this angle is just a reflection of this angle. So therefore, they're both equal to theta. They're both the same angles. And therefore, we have proven our theorem. If you found this interesting, then I encourage you to delve into more 2D Euclidean geometry. I think the world of geometry is a very fascinating field of math to study. It can get quite hard, I would say, but it's really cool. Oftentimes, the proofs are very elegant. Anyway, thank you very much for watching this video. If you found it interesting, then please do consider dropping a like and subscribing. Thank you very much. Bye.